Hello everyone, hope you're doing well today. We are Team Phoenix Electric Corporation and today we will be presenting our Capstone project, which was a fiber optic annunciator. Our technical directors that assisted us on our project this year were Sandro Silva and Mike Smith. My name is Seth Patello. I am an electrical engineer and joining me today are my colleagues Maxwell Tyree, an electrical engineer, and Ethan Ribb, also an electrical engineer. Phoenix Electric Corporation, our sponsor company, is based in Boston, Massachusetts. PEC provides customers in the electric power industry with customized solutions and technical services they require to meet their individual power needs. Now that we have some background, I will get into our project. An annunciator is a centralized warning panel composed of an array of LEDs that monitor the status of many components in a machine or system and report that information to one place. In the case of PEC, annunciators are commonly used in electrical cabinets to monitor a set of breakers. A common problem with traditional annunciator systems is they communicate using copper wire between their input board and annunciator board. This copper wire is susceptible to electromagnetic interferences, otherwise known as EMI. These interferences can lead to false positives resulting in unnecessary downtime and costly maintenance fees. This is the main motivation behind our annunciator. Using fiber optics to communicate between our input and annunciator board, our system is significantly more immune to EMI. This immunity grants the system much more reliability. Additionally, a product such as this has high market demand in the power distribution industry. When designing this prototype, we strive to keep the total system under $1,000 to be extremely competitive with other annunciators on the market, which we successfully have achieved with a current cost of roughly $570 for hardware and software we have used thus far. As you can see, our annunciator is significantly cheaper than most other models on the market. On top of this, there is currently no off-the-shelf fiber optic annunciators, meaning if a corporation needed one, they would most likely need it custom made, which would come with a large cost. Our annunciator would also increase power grid safety and reliability by reducing the occurrence of false positives at power substations. Our project's anticipated best outcome was a fully functional prototype capable of monitoring 12 channels and communicating their status via fiber optic to the annunciator panel. As you can see from the diagram on this slide, our ABO was to take in the status of 12 breakers and send their open-close status to the input board and communicate this via fiber optic to the annunciator board, then display to the LEDs whether the status is invalid or valid. We are elated to report we have achieved our anticipated best outcome. As you can see in this picture, we have our fully functional prototype. On the bottom left, we have our breaker PCB, which consists of switches to simulate a breaker panel. We can flip these switches to mimic a breaker tripping. The status of these switches is reported to the input board, then communicated over the yellow fiber optics to our annunciator board, which unpacks the information and displays the valid/invalid status to our annunciator PCB, which consists of 12 LEDs to indicate the status of the breakers. Additionally, the annunciator PCB houses 3 push buttons in order to operate the system. In this picture, 6 breakers are configured for normally open and 6 normally closed, and all the breakers are closed, which is why 6 LEDs are green and 6 are red. On top of achieving our best anticipated outcome, we have also achieved several stretch goals, which include several push buttons, a programmable delay filter, configurable continuity checks, schematics, and a basis for serial port configuration. I'll now pass the presentation over to Maxwell, who will discuss our technical achievements.
The first major component to this project is the fiber communication interface. This interface is the means for each board to send data between each other. This data could be continuity signals going from the input board to be displayed on the annunciator board, or configuration data coming from the annunciator board to be used by the input board. Our fiber interface uses the SFP transceivers included on our evaluation board. We chose the Aurora 8B10B IP from Xilinx, which implements the 8B10B encoding and also handles the clock correction and alignment required for multi-gigabit links. On top of this, we have made a custom protocol which describes the data sent between each board. The header contains information about the source and payload, while the payload could be continuity check signals or configuration data. On the Annunciator board, we need a display driver that mimics the behavior of traditional annunciators. This display shows the status of each continuity check channel and indicates whether each invalid signal has been acknowledged or not. Our display consists of 24 LEDs, 12 red and 12 green. This is divided into 12 channels, each with their own state. A green light indicates normal continuity for that channel and no issue. A blinking red light LED indicates that a new channel has gone invalid. With the press of the Acknowledge button, the blinking will be suppressed, indicating that a technician is on their way, while the Reset button forces all channels to display the current status, intended for when the technician is finished investigating the switches. Finally, we have a Test button that tests all the LEDs with a pattern to make sure that they are working. Our last planned feature was the means to configure the Annunciator system via a USB port. By means of a USB to serial converter, the user could set the programmable delays and configuration of the continuity checks. This would be accomplished by adding a microblaze to our design, which would handle saving the configuration data to the onboard flash memory, and then initiate the transfer of the configuration data from the Annunciator board to the input board. Unfortunately, this feature was not able to be completed due to the complexity of the microblaze core. However, we were able to successfully test the microblaze reference design and package our custom Annunciator IP as a peripheral to be used with the CPU. We are documenting the work done on this feature in hopes that the next team may finish writing and testing the firmware for the microblaze. Next, Ethan will talk about the rest of the important features of our design.
Thank you, Max. Now I'm going to be talking about the continuity check module that you can see on the lower left. So the continuity check module is really performing the main function for the whole system. And it's one of the first things we started working on last fall. And we were able to complete the module and simulate it successfully pretty early on. So I'm just going to talk a bit about what it does and how it works. So one thing you couldn't see in the block diagram was the actual 12-channel breaker that this will be checking the continuity of. The breaker itself is located in a power cabinet at a power substation, and our input board with a continuity check module is inside that cabinet. The design is configurable to check continuity for normally open or normally closed circuit on each channel. For instance, if you look at the diagram, which is very simplified, if this was configured to be a normally open breaker, then the continuity would be valid if we were sending out a high signal at the output and receiving a low signal at the input. If for whatever reason we see a high signal at the input, continuity would be set to invalid and an alarm is sounded for that channel. But you might be asking, what if there's noise or interference in the system somewhere that would sporadically trigger the alarm? To address that problem, we integrated a delay module into the continuity check. The delay module can be configured so that continuity would have to become invalid and remain invalid for at least 1 millisecond in order for an alarm to be triggered. So it's essentially acting as a debounce module, and it can be configured from 1 millisecond all the way up to 60 seconds. This will drastically cut down on any chance of a false alarm. So as you can see from the block diagram, we needed to be able to take in multiple power sources, so AC and DC voltages, and convert them to lower level DC voltages in order to power our Annunciator. One of the last things we worked on this spring was to determine how the system as a whole would be powered. PEC specified that we would need to be able to take in a wide range of voltages in order to accommodate customers with differing power requirements. These input voltages included 120 and 24 volts AC and 125, 48, and 24 volts DC. These converter modules would also need to have the ability to step down to 3.3 volts in order to power our FPGA modules. We couldn't really find an all-in-one solution to taking in all these voltages. So we decided that the most cost-effective solution would be to find a few converters that could do the job. So we ended up finding 3 converter modules that could basically take in the whole range of required voltages and also had the ability to step down to 3.3 volts. So this way, with 3 converters, only the power modules that are needed for a customer's specific power requirements will be included in the Annunciator, cutting down on costs. And with that, we would just like to thank the Capstone and technical directors that have helped us out along the way. We really couldn't have done any of this without you, so thank you.